So now we can add matrices and subtract matrices. Oh, and we can multiply them by scalars. What about multiplying a matrix by another matrix? What's that going to look like? The easiest way for me to show you what that means is to do it. So let me give you an example. Let's suppose I'm packing ice creams. I have strawberry flavour, banana flavour, and raspberry flavour. Make sure my B and my R look different. And I have a package 1 and I have a package 2. So in my matrix, I might say the first package has 4 strawberry, 5 banana, and 4 raspberry. And the second package has 3 strawberry, 1 banana, and 2 raspberry. And then I'm going to call this one N for the number I have, remembering that these labels on the rows and columns are actually not part of the matrix. And my prices, my price matrix, is going to be about strawberry, banana, and raspberry. And the prices are going to be, let's go $2, $3, and $2.50. Why not? I made my life hard by giving myself decimals. For me to work out the total cost, the total price for package 1 and package 2, I can do a single matrix multiplication. I'm going to go NP. I'm going to write it out fully as matrices, and I'm going to show you how we do the multiplication. 3, 1, 2 times 2, 3, and 250. And here's what we're going to do. We're going to go across the first row and then down the column. And that's going to give us our first element. 4 times 2, 5 times 3, 4 times 250. And then we're going to go back and we're going to go across the second row and down the column. So we're going to go 3 times 2, and we're going to go 1 times 3, and we're going to go 2 times 250. Then we're going to do those calculations. I'm just going to do one extra step to make it clear. 8 and 15 and 4 lots of 250 is $5. And the bottom we're going to get 6 and 3 and $5. Something went very wrong there. What went wrong? Oh yes, 4 lots of 250 is $10, not $5. That's better. Did you spot that before I did? So my resulting matrix is 8 and 25, which is 33, and 6 and 8 is 14. So that means package 1, remember, and package 2. Package 1's total is $33, and package 2's total is $14. Done with matrix multiplication. That's an example. Let's do a couple more examples. Let's make a few matrices first. -3, 7, 2. And B can be 1, 1, 2, 3. Let's do AB. Notice I don't write a symbol for the matrix multiplication. Just like with numbers, you just multiply them. You don't need a symbol for that. So AB is going to be 12, -3, 7, 2. Make sure my negative looks right. And then B is 1, 1, 2, 3. So what I'm going to do is go across the first row and down the first column. So I'm going to get 12 times 1 plus negative 3 times 2. Then I'm going to go across the first row and down the second column. So I'm going to get 12 times negative 3. Nope. Where did that come from? 12 times 1 and negative 3 times 3. Then I'm going to go across the second row and down the first column. So I'm going to get 7 times 1 and 2 times 2. Then I'm going to go across the first row and down the second column. So I'm going to get 7 times 1 and 2 times 3. See how I'm doing that? Which is going to give me 12 take 6, which is 6. 12 take 9, which is 3. 7 plus 4 is 11. 7 plus 6 is 13. Notice how, let me try highlighting this. Notice how this top left element came from the first row and the first column. This element here, which is in the first row, second column, came from the first row and the second column. And so on. Come on. Come on, there we go. This element came from, it's in the second row, so it came from the second row. It's in the first column, so it came from the first column. And finally, the last one, it's in the second row, so it came from the second row. It's in the second column, so it came from the second column. Okay, let's try something slightly different. Let's investigate whether matrix multiplication is commutative. What's BA? Well, let's write the two matrices out. 1, 1, 2, 3 times A, which is 12, negative 3, 7, 2. And again, we're going to go across the first row, down the first column. So we're going to get, do I still need to write that? Maybe I do. Let me go, what did I use? Green first. So we're going to go across the first row and down the first column to get the first element in that matrix. 1 times 12 plus 1 times 7. Then we're going to do orange. Then we're going to do across the first row, down the second column. So we're going to have 1 times negative 3 and 1 times 2. Do I need to keep highlighting? Maybe I'll do it one more time. Let's go yellow. We're going to go across the second row, first column, in order to get the result in the second row, first column. So that's 2 times 12 plus 3 times 7. And finally the last one, which I did last time as pink, is going to be second row, second column. So that's going to be 2 times negative 3 and 3 times 2. So I'm going to get 12 plus 7, 19. Negative 3 plus 2, which is negative 1. 24 plus 21, 43. That didn't work. That wasn't right. 45. 24 plus 21, 45. Negative 6 plus 6 is 0. Now notice something. This is not equal to AB. Matrix multiplication is, in general, not commutative. In fact, we can go a step further. Because of the way this process happens, there are actually some times when you cannot multiply matrices. Let me show you what I mean. What happens if I try to multiply this new matrix C by A? I've got 7, 0, 12, negative 3, 7, 2. That was a 7. You ready for the problem? Can you see it yet? Let me go across the first row and down the first column. 7 times 12 plus, what times that second 7? There's nothing left here to multiply by this 7. I actually cannot multiply these matrices. It is not possible. Because of the way the matrices are set up, if I have an m by n matrix and I multiply it by an n by p matrix, I'm going to get an m by p matrix. Look at how that works. This many columns, the columns on the first matrix here, have to correspond to rows on this matrix. These must equal. Otherwise, I cannot multiply them. The result depends on the number of rows in the first matrix and columns in the second matrix. That gives me the size of my result. So I cannot do C times A, but I can actually do A times C. Because, let me write them out, 12, negative 3, 7, 2, times 7, 0. Notice now, this matrix here has 2 columns and this one has 2 rows. The one on the left has 2 columns, n is 2, and the one on the right has 2 rows, n is still 2. So I can do this. My result is going to have 2 rows, same as A, and one column, same as C. So we're going to go 12 times 7 plus negative 3 times 0, and then 7 times 7 plus 2 times 0. And that's going to be 12 sevens are 84, take 3, and 7 sevens are 49. When you get better at this, yes, if you wish, you can skip this bit. You don't need to write that extra step once you get good at it. But I encourage you to keep writing it for now until you know what you're doing, until you are very comfortable. Sometimes we can get some really interesting results. So let me show you a couple of really interesting ones. I've got a small column matrix there. Let me give myself a row matrix. 8, 1. Okay, what's this? C times D. Can I do it? Well, C looks like this and D looks like this. Do I have the same number of columns in C as I have rows in D? Yes, they both have 1. But my result is going to have 2 rows and 2 columns. The first element is going to be first row, 7 times 8. The second element is going to be first row, second column, 7 times 1. The third element is going to be second row, first column, 0 times 8. And the fourth element is going to be second row, second column, 0 times 1. Also, I can do D times C. Let me show you that one. That was a very messy square bracket. Let's see if I can neaten that up a bit. D times C is 8, 1, 7, 0. So my result this time is going to have, let's work this out. Can I multiply them? Yes, I can, because this one has 2 columns and this one has 2 rows. So this matches. My result is going to have the number of rows in D and the number of columns in C, which is 1 by 1. It's going to be a matrix with a single element. It's going to be 7 times 8 is 56 plus 1 times 0. So it's going to be a matrix with just a single scalar in it, 56. Notice it's not the same as writing the number 56. It's a matrix that contains a single element, which is 56.